Yes. Hi everyone. I am SS KIRAN. I am dealing course is electromagnetic waves and transmission lines. Okay. Last class I have discussed about electric potential. Okay. And the relation between E and V. E bar equal to minus del V. In this class, I will discuss about energy density in electrostatic fields. Okay. Let's start with heading. Energy density energy density in electrostatic fields. This is also very important topic. Energy density in electrostatic fields. Before going to this concept, first we concentrate on work done in positioning the different types of charges. Okay, different types of charges. Let us consider any three charges in this space. Okay, today's topic is energy density, energy density in electrostatic fields. Okay, suppose we wish to position 3-point charges. This is Q1, okay, located at P1. Another point charge is Q2, located at point 2. And another charge is Q3, located at P3 point. Now, what happened? These three charges Q1, Q2 and Q3 in an initially an empty space. Initially there is an empty space. No need to write all those things. One, if any Q1 from infinity to P1, because the space is initially charge free. Okay, if any charge moving from horizon, this is horizon, just you can treat as this is horizon or any space. If any charge is moving from this place to this place, this place to this place, initially charge is free and there is no electric field in between, work done is 0. This is very important point. The next phase, the charge is moving from Q1 to Q2. Okay, the work done is transferring Q2 from the infinity to P2. This is equal to the product of Q2 and the potential V2. Okay, now Q1 to Q2, again Q2 to Q3. Okay, now what is the actual formula for work done? W equal to QV. Last class I have derived this expression. Okay, this is very, very important expression. W equal to QV, right? Now what happened? For example, I will tell you once again. When no work is required, no work is required. This is very, very important point. There is no work is required to transfer Q1 charge from infinity to P1. Q1 charge from infinity to, very important, some space, infinity to P1, because the space is initially charge free. There is no electric field. Then what about the work done? So what about the work? The work done, W tends to 0. Okay, the second case is the work done in transferring Q2 to work done is transferring Q2 to from infinity to P2. Q2 from infinity to very important discussion, infinity to P2. This is equal to the QV. Now this charge is Q2. The work is implies the charge is actual charge is Q2, which is the product of potential from V to 1 from 2 to 1. Okay, the potential difference there is two nodes. That's why here I will write V to 1 at P2 due to Q1. Product V to 1 here, Q into V. This is the product Q into V to 1 at P2 due to Q1. Similarly, the work done in positioning Q3 at P3 is equal to Q3 into, again the next step, Q3 work done, Q3 work done, the same multiplication, P3 is equal to the Q3 into V32 plus V31, where V32 and V31 are the potentials at P3 due to Q2 comma Q1, Q2 comma Q1. These two discussions are very important. Now I will take total energy with respect to work done, total energy density. So WE with suffix WE. The first energy, there is two charges, then W1 plus W2 plus W3. Okay. Now what happened? Initially the work done is 0 at W1. Okay. Initially charge free and there is no electric field. Then W equal to 0. Then actual W2 equal to QV. So Q here second charge Q2. Then V means V21 at point 2 due to Q1. Then here I will write QV. Then V21. Right. Then W3 is nothing but Q3 into V. So here two potential differences are due to two potential differences. One is the V32, another one is the V31, respectively Q2 and Q1. Then I will write simply V32 plus V31. Okay, this is the considering Q1, Q2, Q3. Now, for example, if any were positioned, this is called total. The first step is called total work done. Total work done. Okay. The next discussion: if the charges were positioned in reverse order. Super. The charges were positioned in reverse order. Now the expression is converted to WE. The first work done W3 plus W2 plus W1. Okay. Now initially there is no work done, 0. The next one Q2 with respect to V2 3. The next one Q1 with respect to V1 2 plus V1 3. These are the three charges where V23 is the potential at P2 due to Q3. V12 and V13 are respectively the potentials at P1 due to Q2 and Q3. So this is just treat as expression 1. Okay, sorry. This is expression 1. This is expression 2. Now extended to just adding these two equations 1 and 2. Just you can add in these two equations. 2WE equal to the first expression is Q2 VT1 plus Q3 V32 plus V31. Okay, just write all the expressions. There is one final expression is there, that is called Q1 plus V12 plus V13. Just write in order, in sequence. V13 plus V12 plus V13. The next one is Q2. The next one is Q2. Then we can write just Q2. This Q2 is common. VT1, V21 plus V23. Then write as it is Q3. Q3. 1 second. There is a mistake is there. Q3 plus V32 plus V31. Okay, these are the expressions while adding these two work done. Finally, just we can write V12 plus V13. This V12 plus V3, I can write V1. So V21 plus V23, I may write V2. Then V32 plus V31, this is V3. Now finally, 2WE equal to Q1 V1 plus Q2 V2 plus Q3 V3. Okay. Now this is extended to somewhat. Now we may write like this: WE energy density. WE equal to 1 by 2 within the brackets Q1 V1 plus Q2 V2 plus Q3 V3. That's it. Okay. This is the expression where V1, V2 and V3 are total potentials at P1, P2 and P3 respectively. Now I will write in the form of sigma. There is a better understanding. Now finally, this may write with the help of sigma 1 by 2 sigma k equal to 1 to n qk with respect to vk in joules. Right? Now, if I considered some other parameters with help of line, surface and volume, I may write like this. For example, if it is line, I will write 1 by 1. Listen carefully. Now, okay, W work energy, W equal to 1 by 2 integral rho L with V Q. Q means rho V dV, rho L DL, rho S ds. Okay, then this is also an expression with respect DL. This is called line charge. The next expression WE equal to 1 by 2. I may consider rho S V with respect to ds. This is called surface charge. So ds means surface charge. The next one, WE equal to 1 by 2 integral rho v dv. At the same time, v is very qv. This is for q, and we can write v. V here potential with respect to volume dv. So this is very, very important expression. Please concentrate this one. Okay, WE equal to 1/2 integral rho v dv. Okay, right. I will save this slide. Now, finally, in Maxwell's first equation or Gauss law, then rho v. What is the meaning of rho v? Volume charge density. The Maxwell's first equation or Gauss law expression. Del dot d bar equal to rho v. Now substitute this del dot d bar in this expression. This expression I may call. So actually this is third expression. So now no need to give a names of these two expressions, line surface, but we have to give a name for this volume. This is expression 4. Now in this expression 4, substitute del dot d bar equal to rho v. So in the place of rho v, I will substitute del dot d bar. Okay. Now what happened? Work done WE equal to 1/2. There is a integral rho v means del dot d bar. V is also there, potential, and this is volume. Now better you can go with the small brackets. There is a bracket is there, and with respect to v and the volume dv. Okay. Now here we follow some identities we discussed in the vector calculus. Very simple identity. Here I will take one example with respect to a. Del dot va, we may write a bar. This is a bar dot del v, plus v into del dot a bar. This is very, very important expression. So same we can apply this one also. I will extend to this expression. For example, del dot v into d bar. Now I will write d bar dot del v plus v into del dot d bar. Okay. Now what happened here? V into del dot d bar. I will substitute this del dot v into d bar minus d bar dot del v. Okay. That will be tricky, but just you concentrate, then it will be very, very easy. Finally, W equal to energy density and electrostatic fields 1/2 with integral this del dot d bar v. I will substitute this expression del dot vd bar with respect, as it is, there is a volume that is called dv minus, and I will go another one. So this is here plus right hand side. If it is from LHS side, there is a minus. This is 1/2 is common. 1/2 integral 1/2 integral this d bar dot del v with respect dv, with respect to dv. Now very simple. Now I will go with this is del dot d bar or del dot a bar or del dot vd bar with the dv. If I apply divergence theorem, what divergence theorem said that surface to volume. Now here I will convert to volume to surface. Okay. Now del dot vd bar with respect to dv tends to just double integral. This is triple integral. Then double integral. No need to write double and triple integral. Simply we can write VD into DS. Okay. Fine. Now I will go with the regular expression. Okay. Now apply divergence theorem. So here I will write for this expression divergence theorem. Now what happened? W E equal to 1 by 2. W E equal to 1 by 2. Now apply divergence theorem. This del dot VD bar. Now finally this converted to DS. VD bar with respect to DS. With respect to DS. Then 1 by 2. 1 by 2. This is as it is, d bar dot del v with respect to dv. Now here there is two terms in RHS side. One is the VDS into ds. Now this expression has to be reduced. This expression has to be reduced with the help of small theoretical part. For example, there is V is there in this V expression. Already I have discussed in the last lecture. There is a result is 1 by R. Then coming to D bar, the result is 1 by R square. If it is multiplying, this is tends to 1 by R cube. Okay. Now what happened? This ds, ds means some dx into dy or dl into db, whatever it is. So ds is nothing but it is nothing but r square. Okay. Now what happened? This v in the form in the place of vd bar and ds. When vd, v means 1 by r, d bar means 1 by r square. In the expression 1 by 4 pi epsilon naught into 1 by r. This is also 1 by 4 pi 1 by r square, right? So doing some mathematical part, this 1 by VD bar can write 1 by r cube, then ds bar, then r square. The resultant is 1 by r. So I think this is the infinite space. So if I substitute in the place of r in the place of infinity, this total ds is because of this large, this term becomes to 0, or we may reduce or we may neglect this term, because if you substitute r in the place infinity, 1 by infinity is tends to 0. Now the expression is reduced to we equal to actually there is one more extension is also there. Okay, I will write down. I will write here minus 1 by 2 integral there is d bar dot minus del v. Actually there is a relationship between e bar in the place of minus del v. If I substitute with the place of del v, there is minus e bar. So there is minus e bar means minus get. Okay, I will write here minus e bar within the brackets. Then as it is, there is dv. Now finally, then minus plus get cancelled. Now integral 1 by 2 as it is. There is no change. Okay. Now d bar means electric flux density. Then d bar equal to epsilon e bar. Now substitute in the place of d bar epsilon e bar. At the same time, and another e bar is already existed with the help of this del v. Now the second thing is dv volume is as it is. So what happened here? Here the final expression we is equal to means energy density w equal to of 1 by 2 epsilon integral 1 by 2 epsilon here you can consider this free space epsilon naught e square with respect to dv. Okay, this is one expression that is W. Okay, I will take one box. This is the final expression. Okay, that is called W equal to 1 by 2 epsilon naught E squared. Now, if we can define electrostatic energy density, actually there is joule per meter square. Doing some mathematical part. Then finally, if I differentiate with respect to dV, then what happened? The final expression, I will erase this one. Okay, now dWe with respect to dV, so the expression is of actually, if I'm not doing d bar with the place of e bar, so final expression is first I will write the final expression e epsilon naught with e bar square. Now this is extended to e bar in the place of d bar square. Now I will write one more extension, d bar square of as it is, by epsilon naught. Okay, these are the discussions about energy density in electrostatic fields. Okay, the final expression is WE equal to 1 by 2 integral epsilon naught E square with respect to volume dV. Okay, thank you so much. Keep watching. Thank you.